Hello friends, you are watching ERUDIRE PLUS, the professional CAD/CAM solution provider. Let's get started.
Hello friends, today I'll show CFD analysis, parametric study and optimization of a simple heat transfer problem. It is consisting of a fan and a heat source. At the top of heat source, some fins are provided to have a better cooling. From the extreme left hand side, the fan will be used to provide forced air that will be passing through these fins. In this analysis, heat will be transferred from bottom surface and it will suffer conduction and convection both. Initially, heat will be transferred from the surface to these fins, and by forced air it will be suffering convection. And in this analysis, we want to see the temperature at the exit surface. After this simulation, we have to go for some kind of parametric study by varying the input variable. In this case, input variable will be the fan speed, right? After getting the results from parametric study, we'll go for some kind of optimization. Okay, so without wasting time, let us start this analysis. The analysis environment will be initiated with the wizard itself, so we can start from the wizard. Default name of the project is project 3. We're keeping the unit as SI and temperature will be degree centigrade. Next, it will be an internal analysis and heat conduction in solids will be there. Gravity will be definitely involved and the direction of gravity will be Y. So along Y direction it will be minus 9.81 meter per second square, and along Z direction it will be 0. And definitely rotation will be involved because the left hand side fan will be rotating at different speeds, and based on the speed of the fan we'll get different temperature at the exit right ends. Okay, next, gases, we'll consider air as the main gas. Next, container is made up of aluminum alloys. Let us consider aluminum 6061 alloys. Next, default outer wall thermal conditions and roughness we are considering. Next, thermodynamic parameters, it will be atmospheric pressure at 20 degrees centigrade. Solid temperatures also should be 20 degrees centigrade. You can see the direction of flow, it will be along Z direction, so we have to change the axis. Coordinate system will be Z. Okay, let us finish this. Recognizing the fluid volume, it is done. Next one, we have to apply some initial conditions and boundary conditions. For applying initial conditions and boundary conditions, first of all we have to see the computational domain. This is the computational domain. We have to make it a little bit bigger because to ascertain that all parts of the model is inside this domain. Let us drag this one a little bit to ensure that all parts of the model is inside this domain. Nothing should be outside. It is done. Green check. Now we can hide this domain and we have to apply initial conditions and boundary conditions. For applying boundary conditions and initial conditions, it is always suggested to have a segmented view of this model. So we can cut this model along right plane. Green check. Initially you have to provide that fan speed. Now, providing the fan speed, we have provided one dummy space or dummy volume for this fan that will be capable of rotating with a specific RPM. Okay, actually at this moment the dummy volume is hidden. We can see this from the geometry itself. The fan space is hidden. We can make it on. This is the fan space, you can see. Now that one will be capable of rotating. We have to provide boundary conditions. From this right plane, it is not suitable to apply boundary conditions better way. What we'll do is, for selecting the sink location, for selecting the heat surface, we have to cut this one along top plane. So we can cut it along top plane and drag it a little bit as per our requirement. This is the top plane. We can drag this little bit up and see the bottom surface of this heat source. Okay, let us see from front view. It will be easier to understand. It's not cut properly. We can drag it a little bit down to see the exact surface of this heat source. This is the heat source. We can change the view. Now it is visible. We can apply this surface as the heat source. Okay, so we can cut this object as per our requirement to apply initial conditions and boundary conditions in a better way. Okay, so surface is obtained. We can apply initial conditions and it will be surface source. Select that surface. It will provide heat at a rate of 10,000 joules per second. That means heat source will be producing heat at a rate of 10,000 watt. Go and check. Next one, we have to provide fan speed. You can see the complete view of the model. Now rotating regions. Insert rotating region. This rotating region is considered as a fluid and you have to provide a rotation of 1000 radians per second minus 1000 radian per second. Minus will be deciding the direction. You have to select that rotating surface. You can select it from the geometry. Fan space selected. So it will be rotating with 1000 radians per second in a clockwise direction. Green check. Next one, we have to apply boundary conditions. That means extreme left hand side and right hand side, it will be having atmospheric pressure at two extreme locations. So before applying this last set of boundary conditions, we have to cut this one along some specific plane. Let us cut this object along right plane. Green check. Now we can select boundary conditions. Insert boundary condition. It will be environmental pressure, or you can say this is static pressure at the extreme left and extreme right location. Selected. Green check. So all the boundary conditions are applied. Next one, we have to select some goals. Let us select one global goal and one surface goal. Insert global goal. From global goal, we want to have maximum temperature inside this object or inside this container. Let us take maximum temperature inside this object as one of the global goals, and we'll select another surface goal, that means average temperature of fluid at the exit location. Green check. Let us run this. Let us start a new calculations. We can see the solver window has already started iterations. Mesh preparation and model preparation is going on. Let the iterations move on. Whenever it is finished, we will go for further studies and analysis. Iterations are over. We can see the solver is finished and the maximum total temperature is 991.67 degrees centigrade. This is obtained as a global goal, and as a surface goal we can see the average temperature at the exit surface extreme right hand side is 109.19 degrees centigrade. So we can see huge reduction in temperature at the extreme right hand side, and this was possible because of the fan rotation, right? So in this analysis we provided a fan rotation of 1000 rpm. In the next analysis with a parametric study, we'll go for different input variables and see the temperature at the exit surfaces. Okay, now we'll see the different cut plots and dynamics of flow particles also. Let us close these things. Results, we want to see the cut plots. Insert cut plots. You want to see temperature of fluid across right plane. Green check. You can see temperature distribution. Before this heat source, you cannot see that much of variation in temperature, but after this fins, you can see some difference in temperature. Let us play this cut plot. You can see by the application of fan, cooling is going on, and that's why we are having less temperature at the exit surface. You can see this cut plot from front plane also. Let us clear and hide this part, and we'll see from front plane. Cut plots, insert. You want to see from front plane. Okay, green check. Let us see these things from this side. Let us play. Let us clear and hide this part. To see the flow particles inside these fins, we have to make this fin transparent. So we'll make this as transparent. First of all, we'll make the complete view of this model, and we want to see the fins as transparent. Let us select the fins, and we want to make this transparent. Now the fins are transparent, we can view the dynamics of flow particles. Even the fan also we can make it transparent. Fan space, let us make it transparent. Okay. Now we can see the dynamics of flow particles in a better way, right? So we'll see the surface plots right now. Surface plots, we want to see along all surfaces. You want to see pressure, temperature, etc. Initially we'll see temperature of fluid along all faces. Green check. Across the surface we can see different grades of temperature indicated by different colors grades. At the extreme left hand side, temperature is very less. It is in the range of 19 to 20 degrees centigrade, and as it is going from left to right, temperature is increasing. And because of cooling effect also, we can see the temperature at the extreme right side is little less. You can see the temperature at the extreme right hand side, it is also very less. Okay. And at the fins locations, the temperature is very high. It is in the range of 991 degrees centigrade. Okay, fine. Let us clear and hide this part. Next, we want to see dynamics of these flow particles. That means how the air particles will be moving from left to right. So let us cut this one from right plane and see the trajectories, flow trajectories. Insert flow trajectories. Instead of 20 numbers, we can make this as 60 numbers, and instead of pipes, we will see in the form of arrows. Let us select the entry and exit locations. Selected, green check. Now the particle study is going on. You can see the dynamics of flow particles. Let us see the complete view of the model, and let us play these things. Flow trajectories, let us play. It is clearly visible that from the extreme left hand side, fan is forcing out cold air and it is passing through this fins and cooling is going on. And some kind of circulatory motion is observed at this location. That is not wanted, that is unwanted actually. The circular motion at this location is unwanted. Some kind of void is created at this location. You can see. From different locations you can see the dynamics of these flow particles. Okay. Let us clear and hide this part, and next one we want to see the goal plots, which one we have already seen from the solo window itself. Now goal plots, insert. You see both the goals. Let us show these things we have already seen. Let us view all these things in the form of graph from history. First one is total temperature obtained from the global goal. The maximum temperature at the fin surface is equal to 991.67 degrees centigrade, and next one is the average temperature at the exit surface. After 62 numbers of iterations, temperature at the exit location is 109.19 degrees centigrade. Okay, next we'll perform one parametric study, and in this parametric study we'll vary the different input variables. That means we'll vary the speed of the fan and see the different temperatures at the extreme right location. Okay, so solve new parametric study. Initially, we're going to start one design of experiments and optimization. That means we want to have different sets of temperature at the exit surface based on different input variables. Okay, and in this case, input variables will decide from the boundary conditions itself. Let us select those simulation parameters from the boundary conditions. It will come from rotating regions, and for the rotating regions we have a specified angular velocity. Green check. We have to define this one right now. Initial value was minus 1000 radians per second. Now we have to change this value. We are specifying a velocity of minus 1000 radians per second to minus 100 radians per second. You have to select some goals. It will come from output parameters, goals. We can select all the goals. That means maximum temperature of fins and average temperature at the exit surface also. We are selecting both the goals. Let us select the scenarios. We are selecting 5 numbers of experiments with different input variables. Let us create those design of experiments. This is done. We can see at different angular velocities we will get different goals. Okay, let us run these iterations. Now from these iteration results we will get some kind of idea at what speed what will be the temperature at the extreme right hand side surface. Okay, based on that we will minimize this gap and we will go for some kind of optimization. Let the iterations run. It has already started iterations. Let the iterations move on. The solver window has finished all its 5 iterations. We can see the parametric results. At different input variables we got different results. As expected, we can see at maximum speed the temperature at the exit surface is very less. When the velocity is 2575, the maximum temperature of fluid is 894 degrees centigrade, and at the extreme right surface temperature is 74 degrees centigrade. When the angular velocity of fan is 7525 radians per second, in that case maximum temperature is 698.78 degrees centigrade and surface temperature at the exit location is 75.4 degrees centigrade. When the angular speed of fan is very less, like when it is minus 100 radian per second, then the temperature of the fin is maximum. It is 959.47 degrees centigrade, and at the exit surface at the right end it is 100.58 degrees centigrade. That means with minimum angular velocity cooling rate is less. That's why we are having more temperature at the exit surface, by the same time on the fin also. Similarly, you can see when the angular velocity is 5050 radians per second, maximum temperature is 797.78 degrees centigrade, and exit right surface temperature is 55.7 degrees centigrade. And finally, when the angular velocity of fan is maximum, that is 10,000 radians per second, in that case you can see maximum temperature is 920 degrees centigrade and the extreme right hand temperature is 125 degrees centigrade. From this parametric study, it is obvious that if you want to have a temperature at the exit surface to be 100 degrees centigrade, in that case we have to have the fan speed, that is angular velocity of fan, should be near about 100 degrees centigrade. Okay, so next case we can go for goal optimization with a specified range of input variable from 100 radian per second to 120 radian per second, and finally we'll get the exit temperature to be 100 degrees centigrade. Okay, for timing short we will not do this one, but it can be done. So this is all about our today's video regarding CFD analysis and parametric study of a simple heat transfer problem consisting of fan and a heat source. Okay, if you like this video, please subscribe and share, and if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye.